Alright, so we are now moving on to section 2 and section 3. We are going to talk about entropy of the universe. And we are going to talk about how temperature plays a big part in entropy. Okay? So like I was saying, in regular chemistry, we just kind of talked about entropy of the system, which was just a small piece. Today we're going to talk about entropy of the system and entropy of the surroundings. Add them together and you get entropy of the universe. Okay? So, the first, or the second law of thermodynamics says in all spontaneous processes, there's always an increase in entropy in the what? Does it not say it in your notes?
Of the universe.
The universe. This is the key here. So, is it possible for the system to becoming more ordered and it still be spontaneous? Yes. Let me give you an example. No, that's not an example. Yes, it is an example. Liquid freezes on its own less than 0 degrees Celsius, right? Is it going from a liquid to a solid becoming more ordered? Okay? And that's spontaneous. Below 0 degrees, it will spontaneously change from liquid to a solid. Okay? So you're probably thinking, somehow in there, the universe increases in disorder. We will talk about how to figure that out today. Okay? So there's two parts, and this is what the equation tells us. If we take the entropy of the system and the entropy of the surroundings, add them together, we will get the entropy of the universe. Because the system's one specific thing you're talking about, the surroundings is everything else. So you add those two things together, you get the universe. Now, these two things usually are opposites. What I mean by this is if the system increases in entropy, the surrounding usually decreases in entropy. Okay? And this is how you can get water, or going from a liquid to a solid spontaneously, if the surroundings has a bigger impact than the system does.
When it solidifies, it releases energy. Right, when it settles for more, yeah.
And it's releasing energy to what?
Surroundings.
The surroundings. Isn't that going to make the surroundings move faster?
Yeah.
Isn't that going to make it more disordered?
Yeah.
Okay, so we will talk about the main reason or the main way to think about the surroundings has to do with exothermicity. We'll talk about that. But sign conventions, you should remember this, I think, right?
Yeah.
Oh, we kind of talked about it yesterday,
Yeah.
but I was specifically talking about the system yesterday. Okay, but it's still the same sign convention is true. Okay, if I have a positive entropy of the universe, it is going to be spontaneous. Your universe is becoming more disordered. If I have a negative entropy of the universe, it is non-spontaneous, or you would say the reverse reaction happens naturally or spontaneously. Does this happen very often? Probably not, other than when it's at equilibrium. And we know at equilibrium, neither's favored, right? So if neither is favored, it would make sense that you have the entropy of the universe is 0. Okay, it's an interesting characteristic about the relationship between equilibrium and entropy. So, read this. What do you think? living cells, large molecules are assembled from simple ones. Is this process consistent with the second law of thermodynamics?
There are two answers here.
Okay.
Yes and no. Which one of them is the correct one? I do not know. I guess,
Okay, what do we
without more information, I'd say no.
Sure, there has to be something that you would know, right? I
Right.
agree. If, in order for this to happen, what would have to be true?
There's an outside source of energy.
Alright, so here's our equation. If this is our system, right, the living cell is taking large molecules, or taking simple ones and making larger molecules, becoming more ordered, you would say that the entropy of the system is probably what for a sign? Everybody agree with that? Negative? Okay? So the only way for this to happen spontaneously would be what?
Is it positive?
For positive and greater. Does that make sense? The only way for this to happen spontaneously, or favorably, is if the surroundings entropy is positive and greater. And we will, again, we'll talk about each of these as we progress here. Just want to make sure you guys understand that there are two factors here. And in regular chemistry, we just focused on the system. But that's only a small piece. So. The rest of today will mostly be focusing on the surroundings because it's the one we're least familiar with when we're talking about entropy. It says the central idea for determining entropy changes of the surroundings are primarily determined by what? That's kind of what Ryland was kind of getting at. Okay? When he said that, shoot, what were we talking about?
Cells, energy.
No. When you were saying, and I said, an exothermic reaction, energy is released to.
What were we talking about? When water freezes.
Oh, yes. Yes. Okay? So, let's say we have this reaction. Okay? From a system standpoint, I have a mole of liquid that is going to occupy about 18 milliliters of volume. And if I have a mole of gas, it occupies 31 liters of volume. So from a system standpoint, what is true? From an entropy of the system. Okay? Yeah, yep. So I'm going to change an S of the universe. We would say that the system is becoming what?
Less order.
Okay, less order or a positive change in S.
What does that say this 8
This? Milliliters.
Oh. So why is the other one?
Because a gas occupies
okay.
more volume. Does that make sense?
Yeah.
So what I'm saying on this here is that you have liquid converting to a gas. Just think of boiling, right? That process from a system's entropy standpoint is favorable. Okay? Well then, from a system standpoint, why isn't liquid turning a gas at all temperatures? Right? It's only at a certain temperature where liquid spontaneously turns into a gas, right? Above what temperature? 100 degrees, right? If you're at 100 degrees or above, the temperature or the reaction of a liquid going to a gas is spontaneous, but if you're at 100 degrees or below, it's not. Okay? You see what I'm saying here? So yes, if we just look at the system here, it's always favorable, always spontaneous. But remember, the second law of thermodynamics is this positive or not? Okay? So the temperature actually has an effect on this. Exothermicity is an important driving force for spontaneity. So I want you guys to open up your books here. This one page on page 781. This might be the best page of the whole book. It's a bold statement, I know. 781. Okay? Before we get into reading this, let's think about the surroundings when we talk about exo and endo. If you have a reaction that is exothermic, what does that mean for the system? It's releasing energy. What does that mean for the surroundings? It's gaining energy. So an exothermic reaction will make the surroundings will gain energy. If the surroundings gain energy, what do you think the sign of the entropy of the surroundings is going to be? Done?
Yeah.
Wow.
I don't like these pants.
Soccer, the girls' soccer.
Why are you guys laughing?
I'm assuming they're warm now.
Okay? An endothermic reaction. What happens to the system? It gains. Okay? Well, where does it gain it from? Surroundings. So the surroundings will what? So, I want you guys to make one connection here that's pretty important. The sign of S of the surroundings is opposite the sign of the system's entropy. They oppose each other. This, from a system standpoint, okay, is favorable from an entropy standpoint. But from a surrounding standpoint, is this favorable? What is the surroundings doing to go from a liquid to a gas? Yeah, the surroundings are giving energy to the system. So if the surroundings are losing energy, you would say that that's making it more ordered, right? Okay? So they oppose each other. Now the driving force then, or the way to determine whether or not it's spontaneous or not, has to do with what the temperature is. If it's at 100 degrees or above, it's spontaneous. If it's at 100 degrees or below, it's what? Not spontaneous. Okay? So, and that's what this is saying. The central idea of entropy changes for the surroundings are primarily determined by energy flow, whether it's exothermic or endothermic, but also on the temperature. Now, if you read this, it says, the impact of the transfer of a given quantity of energy as heat to or from the surroundings will be greater at lower temperature. So what it's saying is if you have an exothermic reaction, it's likely to be more favorable at a lower temperature. Okay, let me give you an example. The reverse of this, going from a gas to a liquid. That would be, going from a gas to a liquid would be,
Condensation.
yes, I lost it there.
It would be exothermic to the system. Maybe endothermic to the system. Exothermic for. Sorry, no. Exo for the system, endo for the surroundings.
Okay, just let me think for a second. Going from a gas to a liquid would be exothermic, making the surroundings gain energy. Make sense? Everyone? Going from a gas to a liquid, okay? High energy to low energy, energy is given off, okay? The surroundings gets it. Now, if the surrounding is getting a whole bunch of energy, it's more likely to be favorable at a lower temperature than at a higher temperature. So at 100 degrees or lower, condensation happens, right? But at 100 degrees or higher, condensation doesn't happen. Okay, so let me read this because it kind of gives a good analogy as how this works. So in the middle of 781, I'm going to start reading at the word since. It's the second paragraph. Okay, it says, since the change in S of the system and change of S of the surroundings are in opposition for the vaporization of water, that's this, liquid to a gas, the temperature must have an effect on the relative importance of these two terms. What two terms am I talking about here?
System and surroundings.
System and surroundings. To understand why this is so, we must discuss in more detail the factors that control entropy changes in the surroundings. The central idea is that the entropy changes in the surroundings are primarily determined by heat flow. In an exothermic process in the system increases the entropy of the surroundings because the resulting energy flow increases the random motions of the surroundings. We talked about that. Exothermic means you're giving energy to the surroundings, making them speed up, giving them more entropy. This means that exothermicity is an important driving force for spontaneity. In earlier chapters, we have seen that a system tends to undergo changes from that lower its energy. Did everybody catch that? Things bond to what? Become stable, and that means what? Low energy. Okay? We now understand the reason for this tendency. What's the reason? Going to low energy, that's usually exothermic, right? What does exothermic do to the surroundings?
It gives energy.
It increases the entropy of the surroundings. It's part of the piece here. When a system at constant temperature moves to a lower energy, the energy it gives up is transferred to the surroundings, leading to an increase in entropy there. The significance of exothermicity as a driving force depends on temperature at which the process occurs. This is why we say things boil at a certain temperature and above and condense at a certain temperature and below. So determining whether it's spontaneous is at what temperature. And that's what this is referring to. Okay? That is, the magnitude of change in S depends on the temperature at which the heat is transferred. And they give an analogy here that actually is pretty helpful. We will not attempt to prove this fact here. Instead, we will offer an analogy. Suppose that you have $50 to give away. Giving it to a millionaire would not create much of an impression. A millionaire has a bunch of money to spare. However, to a poor college student, $50 would represent a significant sum and would be received with considerable joy. The same principle can be applied to energy transfer via the flow of heat. If 50 joules of energy were transferred to the surroundings, that would be exothermic, right? The impact of that event depends greatly on the temperature. If the temperature of the surroundings is very high, the atoms there are already rapidly moving very fast. The 50 joules of energy would not make a large percent change in their motion, would not make them a significantly change the percentage of their entropy much. On the other hand, if 50 joules of energy are transferred to the surroundings at a very low temperature, where atomic motion is slow, the energy will cause a large percent change in this motion. the impact of the transfer of a given quantity of energy as heat or from the surroundings will be greater at lower temperatures. So what this is saying is exothermic reactions are more favorable at lower temperatures. Because energy is given off in exothermic, right? Giving it to the surroundings, which has lower temperature, and so you're giving energy to the surroundings, which doesn't have a lot of energy to begin with, so when it gains that energy, it has a bigger impact on changing its entropy than if I were to give some energy to something that's already moving really fast. Does that make sense? It's really conceptual, but it's a big piece. Okay, that's why when you go from a gas to a liquid, it gives off energy, right? Right? When I go from a gas to a liquid, it gives off energy. It's spontaneous at lower temperatures, 100 degrees and below, but not spontaneous at higher temperatures, 100 degrees and above. Does that make sense? Okay? It's the idea of giving a lot of energy to something that either has a lot of it or doesn't have a lot of it. Okay? So, in the end here, we got two characteristics here that will help us understand entropy changes of the surroundings. The sign of the surroundings depends on the direction of heat flow. So, what will give me a negative change in S of the surroundings? From a heat flow standpoint. Base it on the system. The system has to be what to give us a negative change in S of the surroundings? Exo or endo? Exo. Right?
So surrounding system, not surroundings.
That makes sense? The system's exothermic, gives energy to the surroundings, making it, ooh, you're right.
Thank you. I was so confused.
I made that mistake. I make mistakes. Does this make sense now?
Yeah, I was.
Yeah. Okay? Negative change in S of the surroundings is a result of what from the system standpoint? Because if the system gains energy, it took it from the surroundings, making its entropy decrease. Sorry for that, guys. Then it says, how big this number is depends on what? Temperature. And that's what we were reading about. We said, yeah, exo means this is positive and endo means this is negative. However, how big this number is has an important impact on the temperature. We said if we give a lot of energy to something that already has a lot of energy, it doesn't have a big effect. But if you give some energy to something that doesn't have much energy, now the magnitude or the amount is important, or is a big, it has a bigger effect. So, before we go any further, I want to give you this equation. I want to write this down for you. When I say exo here, I'm referring to the system and its effect on the surroundings. System's endo, the surroundings gave it up. Right? If the system's exo, the surrounding gains it. That's why you see the positives here and the negatives and how that works. So everybody understand that if the system is gaining energy, it had to come from the surroundings, therefore the surroundings lost it. And if the system is giving off energy, then the surroundings must be gaining the energy. And then per temperature tells us how big this number is going to be.
Then the quantity of heat is of the system. Quantity of heat is heat of the system, right? Or the surroundings.
No, this is surroundings. This exo and endo is just referring to the system. This is the only part that's referring to the system.
Okay.
If the system is this or this, then we have this in the surroundings. And is this number going to be bigger or smaller if this temperature is lower? It can be bigger. So if an exothermic reaction is done at a lower temperature, it has a greater effect on this. That's the money given to a poor person versus money given to a rich person idea. Okay? We can summarize that with this here. Change in S of the surroundings is going to be negative change in H over T. Now, is this change of H, what's that for? What's that referring to? Yes, sorry, that's probably a tough question. It's referring to the system's change in H. Let me explain. Didn't we say that if the system is a negative change in H, that makes it what? Exo or endo? Yes, right? If the system has a negative change in H, it's exothermic. Okay? So if you plug in a negative into this, those two negatives will cancel, giving you a positive change in S. So exothermic gives you a positive change in S of the surroundings. Doesn't that agree with what we've just been talking about? Yeah. If I plug in an endothermic number or a positive number into this, that means the system gained energy, making the surroundings become negative from an entropy standpoint. Okay? So this negative is here. So that the sign conventions work when you plug in a negative change in H for an exothermic reaction and a positive change in H for an endothermic reaction. So last one here. Oops. It asks you, gives you an equation and it wants you to figure out the change in S of the surroundings. So in the first situation, exothermic, right? That means I should get a spontaneous surroundings number, right? A negative change in H over the temperature in Kelvin, 298. Those two negatives cancel out. And I should get 0.419 kilojoules per Kelvin. Look at the sign. What's the sign tell you? What does a positive change in S tell you? We have all kinds of sign conventions, I get it. I'm just talking about whether it's spontaneous or not. Whether it's favorable from a entropy standpoint. More disordered, right? This means the surroundings became more disordered. That's good from a spontaneous standpoint if we're just focusing on surroundings, right? And this should make sense. Exothermic system gives me a favorable entropy of the surroundings, or a more disorder in the surroundings. If you give energy to the surroundings, it's going to be more disorder. That's why you see a positive change in S. If I have an endothermic process, energy came from the surroundings, making it more ordered, so you're probably going to see a negative change in S. Or you will, not probably. I hate to use words and say that this is spontaneous, because this is just one piece of the puzzle. Because the surroundings could be spontaneous, but the system is probably likely to be not spontaneous, so then determining what the entropy of the universe is going to be, it comes down to the temperature. And even though this is not spontaneous from a surrounding standpoint, the system's probably spontaneous. So figuring out what the entropy of the universe is going to be depends on then the temperature at which it happens. Okay, so this is only one piece. The reason why we focus on surroundings today is because every time we talked about entropy up to this point, we usually talk about the what? The system. But to really understand if a reaction is spontaneous has to do with what the system added to the surroundings number is. So you have to know both. Okay?